This is an AS Core Pure question on vectors. Part A. The line L1 has equation x minus 1 over 2 is equal to y plus 1 over negative 1 is equal to z minus 4 over 3. The line L2 has equation r is equal to I plus 3k plus t times by I minus j plus 2k, where t is a scalar parameter. What we need to do is to show that the lines L1 and L2 lie in the same plane. Okay, so the first thing we need to note is that lines are in the same plane if they intersect. So we want to see if L1 and L2 intersect. That's fine. We've got the equation for L1 in Cartesian form and the equation for L2 in vector form. We need them both in the same form so that we can solve them simultaneously. So I can either change the second equation to Cartesian form or change the first one to vector form. I'm going to change the first one to vector form. It doesn't really matter which method you use. There are other methods as well, but I'm just going to take this one and change it to vector form. Now, when we have the equation of a line written in this form here, then we can change it to vector form by picking out these values of a1, a2, a3, b1, b2, and b3. So we can write the equation of L1 as r is equal to, now this is the form it needs to be in, minus the number. So that means that the first value for a1 is going to be 1, a2 is going to be negative 1, and a3 is going to be 4, plus lambda or any scalar, and I just pick out the numbers at the bottom, so that's going to be 2, negative 1, and 3. Now, because I want to work out if L1 and L2 intersect, I need to set the equations or the vector form of the equations equal to each other. So I need to take the vector part of L2, set it equal to the vector part of L1, and solve. So if I take the vector part of L2, that will be written as, so a point that it passes through, that's going to be this part here. So 1 for I, 0 for j, 3 for k, plus, in this case, the scalar is t, and its direction is 1, negative 1, 2. So that's L1, oh sorry, L2. Let's set that equal to L1. So 1, negative 1, 4, plus lambda 2, negative 1, 3. We're now going to take each row and write out the three equations that we get. So the first equation that I'm going to get from the top row is going to be 1 plus t, so I'll just write that as t plus 1, actually, it doesn't really matter, is equal to, on the other side, I'll have 2 lambda plus 1, 2 lambda plus 1. For my second equation, from the second row, I'm going to have negative t, so write it down, negative t is equal to, on the other side here, negative lambda minus 1. So minus lambda minus 1. Now what I'm going to do is I'm going to multiply everything by negative 1 here to get rid of the negatives. I don't need to. I could leave it as it is. It's fine. But I prefer to work with positives. So I should get t is equal to lambda plus 1. Just multiplying everything by negative 1. So write that down. T is equal to lambda plus 1. And then for my third equation from the third row, I will have 2t plus 3, 2t plus 3 is equal to, on the other side here, 3 lambda plus 4, 3 lambda plus 4. Now for the solving simultaneously part, I'm going to start with the first two equations here, and what I'm going to do, I'm going to sub equation 2 into equation 1. And that means just substituting t for lambda plus 1. So I will get lambda plus 1, which is my t, plus 1 is equal to 2 lambda plus 1. So from here I'll have lambda plus 2 is equal to 2 lambda plus 1. Let's take away lambda from both sides. So I'll have lambda and then subtract 1 from both sides, so I'll get lambda is equal to 1. I'm going to take this lambda is equal to 1, substitute into one of my equations to find t. Let's just sub it into 2. So sub into equation number 2, that's the easiest thing to do. So then I will get t is equal to lambda 1 plus 1, which will give me t is equal to 2. Now whenever we have three equations and we've got two unknowns, you must take those values and check it works in the other unused equation. So what we're going to do now is to substitute our lambda equals 1 and t equals 2 into equation number 3. So let's do that and see what we get. So we'll get 2t, so that's 2 times by 2 plus 3 is equal to 3 times by lambda, so 3 times 1 plus 4. And this needs to balance to show that it works in the third equation. So on this side, I'll get 4 plus 3, which is 7 on the left-hand side. And I will get, again, 3 plus 4 is 7 on the other side. So now we can say that therefore lambda equals 1 and t equals 2 satisfies all three of the equations that I wrote down. Therefore the lines L1 and L2 intersect when lambda equals 1 and t equals 2, which must mean that the lines are in the same plane. So that satisfies the statement that we made at the beginning. We could, if we wanted to, go on to work out what the point of intersection is by substituting in lambda equals 1 and t equals 2 into our equations. We're not going to do it just yet. We may need that later on, but that's part A done. Part B, write down a vector equation for the plane containing L1 and L2. So one form of a vector equation for a plane is this form here. R is equal to A plus lambda b plus mu c. Mu and lambda can be different scalars like s and t, for example, where a is a point in the plane and b and c are two non-parallel vectors in the plane. Okay, so a point in the plane can actually be a point in either one of these lines because they are points that are in the plane. We've proved that they lie in the plane. So I'm going to pick this point here. I could easily pick this point here, and in fact I could pick any point which is in either of these lines, including the point of intersection, but I'm just going to pick this as a point in the plane because that's a point in a line and the line is in the plane. So 1, negative 1, 4, you could easily have also done 1, 0, 3 if you wanted to, plus these two non-parallel vectors. Well, we've shown that the two lines L1 and L2 are in the plane, so they are definitely vectors in the plane. Are they non-parallel? Yes, because their direction vectors are not multiples of each other, so these are different directions, so they're definitely non-parallel. So I can use the direction of each of these lines as the non-parallel vectors that are in the plane. So I'm going to pick for my first one the direction of L1, which is 2, negative 1, 3, and then for my second direction vector, I'm going to use the direction of the line L2, which is going to be that 1, negative 1, 2. So there we go. This is one form, and there are many forms of the vector equation for the plane. And lastly, part C, what I want to do is to find to the nearest degree the acute angle between L1 and L2. Now I'm going to be using this formula here to find the cosine of the angle between L1 and L2. Because it says find the acute angle, if you do the modulus of what you have on the right hand side here, that will always ensure that it's the acute angle. If you don't and you get an angle that's bigger than 90 degrees, just do 180 minus that angle that you get. So A and B are going to be the directions of my two lines that I want to find the angle between. So A is going to equal the direction of L1, which is 2, negative 1, 3. And the vector B, that's going to equal the direction of L2, which is going to be 1, negative 1, 2. So these now can be put into the formula. So the cosine of the angle is going to be equal to the dot product of 2, -1, 3 and 1, -1, 2 over the lengths of these angles. So I'm just going to put a big modulus sign around this. Here, I'll put the other modulus sign in once I've got the square root part. So the length of the direction of L1, that's this vector A, is going to be the square root of 2 squared plus -1 squared plus 3 squared, and that it needs to be times by the length of the vector B, and that's going to be 1 squared plus -1 squared plus 2 squared, and that's going to be square rooted like this. So now I'm going to make this fraction line longer and then put my modulus, the second bit of modulus symbol here. Okay, so if we start with the top and work out the top product, so it's going to be 2 times 1 plus -1 times by -1 plus 3 times by 2. So that'd be 2 plus 1 plus 6, giving me 9 at the top. At the bottom, let's work out these. So the square root of 2 squared plus -1 squared plus 3 squared. So that's the square root of 14. And then I'll do the same for vector B, which will be 1 plus 1 plus 4, which will give us 6. And we want to do the modulus of that. In fact, this is positive, so no need to do the modulus. So the angle is going to be the cos inverse of this 9 over root 14 times by root 6. And make sure that your calculator is in degrees, and I get an angle of 10.893 like this. So it's in degrees, it says to the nearest degree, so my final answer will be that the angle between the two is 11 degrees.